Alright, welcome back everybody. In this lesson, in this video, we're going to talk about absolute and conditional convergence of alternating series. And so when we have an alternating series, there are three different things that can actually happen with its convergence behavior. One that is, really strong, and one that is somewhat strong, and then the other is divergence. But we're looking at three possible outcomes here when we look at an alternating series and its convergence. It's possible that the series converges absolutely, which, if you think back, we've talked about absolute convergence before, which means, in this case, the alternating series' absolute value, the series containing the absolute values, would converge. That means that the series converges absolutely. The second possible outcome is the series converges conditionally. That's when the absolute value of the series doesn't converge, but the series itself does converge. And now that we know the alternating series test, we can determine if that happens. And the third possible outcome is that the actual alternating series diverges. Okay? A lot of different approaches we can take to these problems, depending on our gut instincts, but I generally use something that relates to this strategy. I look at the alternating series and I use the nth term test to see if it diverges. If it does diverge from the nth term test, I'm done. I will say that the series diverges. Otherwise, I go and I check, does it converge absolutely? So I take the absolute value of the series and see if that converges. And if it does, then it converges absolutely. If neither of those two work, then I test the alternating series using the alternating series test to see if the alternating series converges. If it does, then that alternating series converges conditionally. And if it doesn't, then that series diverges. So that's kind of my strategy here. So example 1, let's look at this series. Does this series converge absolutely, converge conditionally, or diverge? So the first thing I'm looking at is I'm looking at the limit as a sub n let me try this again. The limit as n goes to infinity of a sub n. Is that equal to 0? If it's not, then the series diverges by the nth term test. But in this case, it's equal to 0, so the nth term test is inconclusive. So I'm going to continue to proceed. Next, I test and see, does the absolute value of this series converge or diverge? If it converges, then the alternating series that we're looking at converges absolutely. In this case, though, the sum from 1 to infinity of 1 over n diverges because it's a p-series with p equal to 1. So this does not converge absolutely. So we've narrowed it down to two possibilities. It might converge conditionally, or it might diverge. It does not converge absolutely. Okay, so then I run the alternating series test on it. Is u sub n greater than 0? Is u sub n greater than or equal to u sub n plus 1? Does the limit as n goes to infinity of u sub n equal 0? And u sub n in this case is just 1 over n. Is that always greater than 0? Yes. Is u sub n greater than or equal to u sub n plus 1 for all n greater than some value? Yes. 1/2 is greater than 1/3, 1/3 is greater than 1/4, etc., etc. Does the limit as n goes to infinity of u sub n equals 0? Yes. So therefore, this alternating series converges, but we've already shown that it does not converge absolutely. Therefore, this series converges conditionally. All right, let's go on to the next example. Does this series converge absolutely, converge conditionally, or diverge? So we try out the nth term test to see if it diverges. The nth term test does not show divergence because this approaches 0. So it's inconclusive, nth term test. So then I'm going to test and see if it converges absolutely. And the sum from n equals 1 to infinity of the absolute value of this series, that's this series here, converges because it's a p series with p greater than 1. So our alternating series here converges absolutely because the absolute value of the series converges. And we don't even need to check. Once we know that it converges absolutely, that's stronger than conditional convergence, so we don't even need to test to see if the alternating series converges. We know that it has to because this series converges absolutely. All right. Example 3. Does the following series converge absolutely, converge conditionally, or diverge? Again, I'm going to try out the nth term test to see and the limit of this as n approaches infinity, a sub n approaches not 0, but 2/3. And therefore, this series diverges. All right. Well, let's keep going. We're doing good. Let's go on to example 4. Does the following series converge absolutely, converge conditionally, or diverge? I'm going to try out the nth term test. And that limit approaches 0. So the nth term test is inconclusive. Then we're going to test and see, does it converge absolutely? So we're concerning ourselves with the sum equals 1 to infinity of n over n to the third plus 2. All right. And I need to determine now if this series converges. And I have a whole tool shed full of tools to help me determine this. I'm going to compare this to the sum from 1 to infinity of 1 over n squared. And using limit comparison, the limit as n goes to infinity of n over n cubed plus 2 over 1 over n squared is equal to 1, which is a finite non-zero value. So, sum from 1 to infinity of n over n cubed plus 2 and sum from 1 to infinity of 1 over n squared share convergence behavior. By the limit comparison test. And sum from 1 to infinity of 1 over n squared converges because it's a p series with p greater than 1. So the absolute value of my series converges, and therefore my alternating series in question converges absolutely. All right, and on to the next page. Example 5. All right. Sorry, I just had to check. I forgot if there were 5 or 6 examples on this lesson. Example 5. Does the following series converge absolutely, converge conditionally, or diverge? we try out the nth term test, limit as n goes to infinity of a sub n. And let's see, that approaches that does approach 0 as n approaches infinity. Yeah. So the nth term test is inconclusive. So then we need to look at the does it converge absolutely. All right. And if I'm looking at this, I multiply this out, I'm going to compare this to the biggest power in the denominator here when I multiply this out is n to the 5/6. So I'm going to compare this to the sum from 1 to infinity of 1 over n to the 5/6. And the limit as n goes to infinity of our series in question here, 1 over n to the 1/2 plus 1 times n to the 1/3 plus 1 over 1 over n to the 5/6 is equal to 1. So by the LCT, these series share convergence behavior. Sum from 1 to infinity of 1 over n to the 5/6 diverges because it's a p-series with p less than 1. So this does not converge absolutely. So then I need to run the alternating series test on u sub n. Is u sub n greater than 0? Is u sub n greater than or equal to u sub n plus 1? Does the limit as n goes to infinity of u sub n approach 0? These are all positive. They indeed do approach 0. Now the only question is u sub n greater than or equal to u sub n plus 1 for all values of n greater than a certain point? I'm going to have to be quick here. And it looks like positive benefits here. Looks like these are all, and since we know they're approaching 0, these are going to continue to decrease. So therefore, this one passes the alternating series test, and our original series here converges conditionally. All right. That's all the examples from the absolute and conditional convergence lesson. Make sure you read the little piece at the bottom here. It's fairly interesting, but not much more than a curiosity for our purposes. See you guys next time. Have a great rest of your day.